So C is equal to F lambda. And C is always the constant, so it cannot change. And so the greater frequency would mean the shorter wavelength. And in the spectrum for electromagnetic waves, here's the visible light. And here's the UV ray. And as it goes here, the lambda decreases. So the only UV is the only ray that has the shorter wavelength than the visible light. So the answer would be the UV ray. This is just math question. The graph is cosine graph, as we can see. So C and D are not the answers. And as it starts from the bottom, the minus sign, we can deduce that there's a minus sign for the expression. So it's A. Okay, so maximum acceleration, and the question only gave us the amplitude. So in the section 9 of the data booklet, on the topic 9.1, there's an equation that A equals to negative omega squared x, and omega is equal to 2 pi over t. So A is equal to negative 4 pi squared over t squared x. So which is equal to, okay, C. So the string is fixed. So the wave is going to be inverted, and as it's being hit by the wall, it is going to lose some of its energy. However, the moving speed v would be constant throughout the motion. It would not change. Only the F lambda, yeah, it's not going to change throughout the motion. The light travels from air into water, so the speed is going to decrease. And as the v equals to F lambda, and the frequency is always the constant for whether the medium changes or not. This one always stays the constant, so it's not going to change. And as the speed has decreased, the wavelength is also going to decrease here. So it's D. By using same equation we used above, A equals to negative omega squared x. So omega squared here would be the constant, so it can be just written as A equals to minus bx, which is the graph for A. This equation is in the subtopic 9.1 in the data booklet. So yeah. Yes, and also the period equation is in the topic 9.1 in the data booklet, which is for the mass spring T equals to 2 pi root m over k. So there's no displacement in this equation, so period is not affected. And the energy is equal to half m omega squared x squared, and x0 is the displacement, and the displacement is doubled, so new energy would be 2x0 squared, so it would be 4x0 squared, meaning that it's going to be 4e. So it's A. this is just memorization question, and this kind of question comes up in the tests really rarely, but it would be helpful if you memorize the wavelength for the visible light. So it's about 600 nanometers to 700 nanometers. So it's just visible light. Okay, refractive index. So equation for this is also in the data booklet. So n1 over n2 equals to v2 over v1. So here 3 times 10 to the power of 8 is equal to 2.7 10 to the power of 8, so it's around 1.1. And you need to remember that the refractive index, the value of refractive index, can never be smaller than 1 because no particle in this universe can travel faster than the light speed. So the force is proportional to F equals ma, and assuming mass is constant, and a is proportional to the displacement. No, there's no squared. So force is proportional to displacement. Equilibrium can be only achieved in the middle position, where the only net force can be 0, because in position X and position Y there would be the net force would not be 0 because there would be tension due to these springs and this spring. Okay, damped harmonic motion. Okay, so energy 1 is equal to half m omega squared x 0 squared, and here the amplitude is 1.5, so half omega squared times by 1.5 squared, e2 half m omega squared times by 0.3 squared, so it's e2 e1 like this. So these cancels out, so 1.5 squared over 0.3 squared, so it's squared, so 1 over 25. Okay, this can be done by measuring the lengths between these, but as I'm using my iPad, I'll skip this question for now. Okay, the wave is traveling to the right, so like after 1 or 2 seconds the wave will look like this, so the P would